Hello friends, welcome to our channel. Today we shall discuss on main topic, that is Leibniz theorem. So first we shall see what is the use of Leibniz theorem. So the first use of Leibniz theorem is that it is mainly useful for calculating the nth derivatives of product of two functions. So now we shall see the statement of Leibniz theorem. So if u and v are the two functions of x, then the Leibniz theorem is given as by the form d raised to n into uv is equal to d raised to n into u into v plus nc1 d raised to n minus 1 u into dv plus nc2 d raised to n minus 2 u into second derivative, that is d square into v plus ncr d raised to n minus r u into d raised to rv plus up to nth term. So that is u into d raised to nv, that is nothing but up to nth derivatives we need to find. So here d is nothing but d by dx, nc1 is nothing but n, similarly nc2 is nothing but it's a combination which is written as n into n minus 1 divided by 2, and similarly NCR, the formula for the combination, that is NCR, is nothing but n factorial divided by n minus r factorial into r factorial. So now we shall see some of the examples. So first we shall consider a simple example, that is x is equal to tan log y. Prove that one plus x square y n plus 1 plus 2 nx minus 1 into yn plus n into n minus 1 yn minus 1. So then we shall find the solution for this. So first the given equation is of the form x is equal to tan log y. So first we shall see how to reduce this. So first consider that if you tan inverse on the left hand side, then it will be tan inverse x. So if you shift the tan on the left hand side, then it will be tan inverse x is equal to log y, or you can write y is equal to e raised to tan inverse x. So then after that, to find the nth derivative, first we need to differentiate the function with respect to x. So first we shall differentiate. So differentiating with respect to x, so differentiating y with respect to x, so differentiation of y, consider the first derivation to be y1. So y1 is equal to e raised to tan inverse x. Differentiation of e raised to tan inverse x is e raised to tan inverse, that is differentiation of e to the power x is e to the power x itself. So differentiation of e raised to tan inverse x is e raised to tan inverse x into differentiation of tan inverse x is nothing but 1 divided by 1 plus x square. So just write 1 divided by 1 plus x square. So this is nothing but e raised to tan inverse x upon 1 plus x square. we know that by the formula y is equal to e raised to tan inverse x. So just replace e raised to tan inverse x by y divided by 1 plus x square. So now this is in the form y1 is equal to y by 1 plus x square. So just shift 1 plus x square on the left hand side. We can write it as 1 plus x square into y1 is equal to y. That is 1 plus x square into y1 minus y is equal to 0. So apply the nth derivative, that is dn of 1 plus x square into y1 minus y is equal to 0. Now we need to apply the nth derivative for this and this. So we shall separately apply. So the nth derivative for 1 plus x square into y1 minus nth derivative of y is equal to 0. So now we shall apply the Leibnitz theorem. So Leibnitz theorem is given by we have written here the Leibniz theorem. So we shall write it once again. So Leibniz theorem, it is given by d raised to n into uv is equal to d raised to n u into v plus nc1 d raised to n minus 1 u into d into v plus nc2 d raised to n minus 2 u into d square v plus ncr d raised to n minus r u into d raised to r into v plus u into d raised to n into v. So now we shall write this equation in this form. So first we shall apply the Leibniz theorem for this separately and then for this next. So first the d raised to n into, so first we need to take u is equal to n, v is equal to. So as we can observe that u into d into v. So here d is nothing but, so the capital D is nothing but d by dx, means you need to apply the differentiation. So if you take u is equal to 1 plus x square and v is equal to y1, then it keeps on derivating. So but you need to stop the derivation. So for that purpose, if you consider v is equal to 1 plus x square and u is equal to y1, so if you consider v is equal to 1 plus x square, so the first derivation of 1 plus x square will be 2x, and similarly if you again derivate, it will be 2. So by further derivating, it leads to constant term, that is 0. So we need to take in such a way that, so d raised to n into 1 plus x square into y1 is equal to, so d raised to n, u is nothing but 1 plus x square into y1 plus nc1. We know that nc1 is nothing but n. So just substitute nc1 is equal to n into d raised to n minus 1. So we have taken u is equal to y1. So just substitute u is equal to y1 into d is nothing but d by dx. So d by dx of v is nothing but 1 plus x square. Similarly nc2. We know that nc2 is nothing but n into n minus 1 divided by 2. So just substitute in place of nc2 n into n minus 1 divided by 2. So then into d raised to n minus 2 into u is nothing but y1, then again d by, that is second derivative, that is d square upon dx square into 1 plus x square. So it keeps on continuing. So then minus, so minus, keep d raised to n into y as it is equal to 0. So now we shall find d raised to n 1 plus x square into y1 is equal to, so then write 1 plus x square into y1 plus, so this is nothing but n into, so here we have d raised to n minus 1 and here we have 1. So plus 1 minus 1 gets cancelled. So just write d raised to, we shall write it later, so y1 into differentiation of 1 plus x square, differentiation of 1 is 0. Similarly differentiation of x square is nothing but 2 into x plus, so then n into n minus 1 divided by 2 into d raised to n minus 2 into y1 into. So we know that the first differentiation is 2 into x. So we need to differentiate again. So differentiation of 2 into x. Differentiation of x is 1. So it is only 2. So plus. So again if you further differentiate, it leads to 0. So differentiation of constant term is 2. So then it is 0. So minus d raised to n y is equal to 0. So then we can write, so 1 plus x square. 1 plus x square into, so we can observe that 1 plus x square into, here we have nth term, so d raised to n and y1. So for n and 1, so here we can write it as yn plus 1 for n terms. So yn plus 1 plus, so keep n into d raised to, so here we can see that d raised to n minus 1 into y1 into 2 into x. So here the 2 and 2 gets cancelled. So we can write it as n into n minus 1 d raised to n minus 2 into y1. So this is plus 0. So then minus. So the nth term we can d raised to n y. So we can write for n terms, it is written as yn is equal to 0. So therefore 1 plus x square into yn plus 1 plus. So we can observe that here we have minus 1 and here we have 1. So it gets cancelled. So just write it as n is there 2x. So it is 2n into x. 2n into x into y. This can be written as yn. So plus. So then we have n square minus n. So minus 2 plus 1 is nothing but minus 1. So just write yn minus 1 minus yn is equal to 0. So therefore 1 plus x square into yn plus 1. So we can observe that we have 2n into x yn and here we have minus yn. So just take yn, we need to take yn common. So just write 2n into x. So here there is nothing, means it is indicated as 1. So 2n into x minus 1 into yn plus. So just write it as, you can also just write n into n minus 1 into yn minus 1 is equal to 0. So this is the required nth derivative for the equation x is equal to tan of log y. You can also write n square minus n, but simply you can also write n into n minus 1 into yn minus 1. Next we shall see one more important problem on Leibnitz theorem. So that is sin inverse y is equal to 2 into log of x plus 1. Prove that x plus 1 whole square yn plus 2 plus 2n plus 1 into x plus 1 yn plus 1 plus n square plus 4 into yn is equal to 0. So we need to prove this equation by applying the Leibniz theorem. So first we shall see how to solve this problem. So initially the given equation is of the form sin inverse y is equal to 2 into log of x plus 1. So first, to apply the Leibniz theorem we need to differentiate the given equation. Then we need to apply the Leibniz theorem. So first differentiating. So differentiating with respect to x. So as we know that the sin inverse y formula. So sin inverse y is nothing but 1 divided by square root of 1 minus y square. So just write differentiating y with respect to x. So sin inverse y is nothing but 1 divided by square root of 1 minus y square into differentiation of y is nothing but it's y1 is equal to 2 into, as we know the formula, that is log x is nothing but 1 divided by x. Differentiation of log x is 1 by x. Similarly the differentiation of log of x plus 1 is nothing but 1 divided by x plus 1. So keep 2 as it is. So differentiation of log of x plus 1 is nothing but 1 divided by x plus 1. So just so we can write it as square root of 1 minus y square into y1 is equal to 2 divided by x plus 1. So then we can also modify this equation. So because we need to prove that x plus 1 whole square. So just take x plus 1 on the left hand side. So we have x plus 1 into y1 is equal to 2 into square root of 1 minus y square. So then we need to prove that the equation x plus 1 whole square, but here it is only x plus 1. So in order to obtain x plus 1 whole square, so we need to square on both sides. So just square on both sides, that is squaring on both sides. So by squaring on both sides, we have x plus 1 will be x plus 1 whole square into y1 square. So you need to square this. So that is 2 into square root of 1 minus y square whole square. So that is x plus 1 whole square into y1 square is equal to, so 2 square is 4 into, so this square root and this square root get cancelled. So it is just 1 minus y square. So next step is again, so we have obtained this. Then we need to again differentiate this again. So again differentiating with respect to x. X. So we can write it as x plus 1 whole square into, so differentiation of y1 square is nothing but, so differentiation, so d by dx, differentiation of x square is nothing but it's 2 into x, right? So therefore differentiation of y1 square is nothing but it is 2 into y1 into, so differentiation of y1 is nothing but it is y2 plus, so keeping y1 square as it is. So we need to apply the u into v form. So u into v, as you know the differentiation, so that is differentiation of u into v. So differentiation of x with respect to u into v is nothing but u into dv by dx plus v into du by dx. So just we have applied the u into v formula. So that is first initially keeping x plus 1 whole square into, so applying differentiation for y1 square, so it is 2 into y1. So differentiation of y1 is y2 plus, so then second term keeping y1 square, so keeping y1 square, then you need to differentiate x plus 1 whole square. So differentiating x plus 1 whole square, we have 2 into x plus 1. 2 into x plus 1. So again differentiation of x, it will be 1 itself. So then again is equal to 4 into, so what about differentiation of 1 minus y square? Differentiation of 1 is constant term is 0. So then differentiation of y square, so differentiation of y square is nothing but it is keeping minus sign as it is, differentiation of y square is nothing but 2 into y. Again differentiating y is, it is y1. So this is the equation we have obtained. So then after that we need to remove the 2, because in this equation, because we need to prove that x plus 1 whole square, and we need to eliminate this 2. So for that purpose we need to divide by 2. So dividing the equation, so then dividing this equation 1. So dividing equation 1 by y1 into y2. So then by dividing the whole equation by y1 and y2, so x plus 1 whole square into 2 into y1 y2, dividing it through y1 y2, dividing by 2 into y1 y2, so 2 into y1 y2 plus y1 square 2 into x plus 1, so again dividing it by 2 y1 into y2. Next 4 to side, so minus 8 into y into y1. So that is 2 into y1. So we can observe that we cannot divide the whole equation by 2 y1 and y2, because here there is y2, here there is no y2. So here also there is no y2. So just divide this whole equation by y2 itself. Just write 2 into y1. So now just by dividing the equation by 2 into y1, so cancel the terms wherever you have 2y1. So here also we have 2 into, so 1y1 will get cancelled. So here 2 4s are 8. So then divided by y1. So therefore the required result will be x plus 1 the whole square into. So just y2 plus. So we have cancelled 1 y1. So remaining is x plus 1 into y1 is equal to. So it is minus 4 into y. So this is the required result. So we shall write it in the form of an equation, that is x plus 1 whole square into y2 plus x plus 1 into y1. So minus 4y, just shift on the left hand side, we have plus 4 into y is equal to 0. So thus we have obtained this equation. So now what we need to do is we need to apply the Leibnitz theorem separately for this equation. So we have obtained x plus 1 whole square into y2 plus x plus 1 into y1 plus 4 into y is equal to 0. So now just apply the Leibnitz theorem separately for these three equations. So that is, apply the Leibnitz theorem, x plus 1 whole square into y2 plus x plus 1 into y1 plus 4 into y is equal to 0. So now we shall separately apply it to all these three. So that is x plus 1 whole square into y2 plus x plus 1 into y1 plus, so apply the Leibniz theorem for 4 into y. So now we shall solve this individually. So first we need to apply for this, then for this, and then separately for this. We know that Leibniz theorem. So now applying Leibniz theorem. So applying Leibniz theorem. For differentiating n times. So as we know that the Leibniz theorem is given as d raised to n u into v is equal to d raised to n u into v plus nc1 d raised to n minus 1 u into d into v plus nc2 d raised to n minus 2 u into d square v plus ncr d raised to n minus r u into d raised to r into v plus up to n terms, so d raised to n into v. So now we shall apply the Leibniz theorem separately for this, and then for this. So then consider d raised to n into u into v. U is x plus 1 the whole square into y2 plus is equal to, so d raised to n. So we need to assume one to be u and another to be v. As we have discussed earlier, we need to take u to be y2 and v is taken as x plus 1 whole square, because we can find the differentiation of this term and we can eliminate the constant term. So then d raised to n. So we have assumed u to be y2. So then y2 into v is nothing but x plus 1 whole square plus, then nc1 is nothing but n, so n into. So what about u? Keeping u y2 as it is, then d is nothing but differentiation, so d by dx. Similarly d square is nothing but d square upon dx square. So just write d by, so n into d raised to n minus 1 into u is nothing but y2. Similarly, so what about v? V is nothing but, so d into v, so d is nothing but d by dx of, so we have taken v to be x plus 1 the whole square plus nc2 is nothing but n into n minus 1 divided by 2. So just replace n into n minus 1 divided by 2. So then we have the next thing is d raised to n minus 2 u. So what about u? We have taken it as y2, so keep y2 as it is. Then d square, so d square is nothing but finding the second derivative, so d square divided by dx square into v. So x plus 1 the whole square. So plus we need to do up until we eliminate the constant term. So this is for the first equation. So we need to we need to apply this for the second terms and also third terms. So then plus d raised to n u into v. So d raised to n. So here also you can take, for the second equation, take u to be y1. So y1 into, so that is y1 into, so what is v? V is nothing but x plus 1 plus nc1 is nothing but n into d raised to n minus 1 into u is nothing but keeping y1 term as it is into first derivation is d by dx of x plus 1. So we can see that the differentiation of x plus 1 is nothing but 1. So again, if you apply the differentiation for constant term, it will be 0. So just stop here itself. So this is second term. Similarly, plus you need to apply for the third equation, that is d raised to n 4 into y. So we can observe that then you need to apply the nth derivative for the 4 into y. So you need to substitute it to 0. So now we can solve this individually. So we can write it as x plus 1 whole square into, so this is yn and this is y2. So just here there is no any negative sign, so it will be yn plus 2. So this will be yn plus 2. So plus, so then we write n as it is. So then d raised to n minus 1 into y2 into, so the differentiation of x plus 1 whole square is there. So differentiation of x plus 1 whole square is nothing but 2 into x plus 1. So 2 into x plus 1. Then after that it will be 2 into x plus 1. So then again if we differentiate, differentiation of x will be 1 and constant will be 0. So then plus. So then keep n into n minus 1 divided by 2. D raised to n minus 2 into y2. Then the second differentiation, that is we know that the second differentiation of x plus 1 whole square. So the first differentiation is 2 into x plus 1. So then the second differentiation, so this is nothing but if you multiply inside it will be 2x plus 2. So then, so constant differentiation of constant term is 0. Similarly, differentiation of 2 into x is nothing but, so differentiation of x with respect to x is 1. So just write differentiation of 2 into x is 2. So again further, if you apply again the third derivative, then differentiation of constant term will be 0. So the whole equation will be 0. So just stop here itself. Plus. So now we need to solve this. So then it is x plus 1 into y1. So x plus 1 into, so you can observe that here it is d raised to n and here we have y1. So it is nothing but for nth derivative you can write it as d raised to n plus 1. So write d raised to n, y raised to n plus 1 plus n into d raised to n minus 1 y1 into. So differentiation of x plus 1 is nothing but differentiation of constant term is 0. So differentiation of x with respect to x is 1. So therefore just write it as 1 into 1 plus. So then differentiation of, so keep 4 as it is. So differentiation d raised to n into y. For n terms it will be yn is equal to 0. So now we shall remove this all. So therefore x plus 1 whole square into yn plus 2 plus yn plus 2. So then, so we can write this. So that is 2 into x plus 1. 2 into x plus 1. 2 into x plus 1 into. So you can see that here we have taken this constant term 2 into x plus 1. So then we can observe here that, so into n is there, so into n. So here we have n minus 1 and here we have 2. So that is minus 1 plus 2. So that is here we have minus 1 and here we have plus 2. So that is minus 1 plus 2 is nothing but it's just 1. So for n terms you can write it as n plus 1 plus. So here we can see that 2 and 2 constant term gets cancelled. So just write. So here also we have n. So n into n minus 1 into. So then here we can see that here we have minus 2 and here we have plus 2. So this both will get cancelled. So minus 2 plus 2 will get cancelled. So just write it as, So we have n plus 1, and then this minus 2 and plus 2 will get cancelled. So just write it as yn plus. So therefore it will be x plus 1 into yn plus 1 plus n into. So therefore this will also be minus 1 plus 1 will get cancelled. So just write it as n into yn plus 4 into yn is equal to 0. So therefore you can write it as x plus 1 the whole square yn plus 2. So just multiply. So just it is 2 into x plus 1. 2 into x plus 1 into yn plus 1. So here we have, so just write plus 2 into x plus 1 into n into yn plus 1 plus. So just write n square minus n into yn. So plus x plus 1 into yn plus 1 plus n into yn plus 4yn is equal to 0. So therefore x plus 1 whole square into yn plus 2. So you can observe that we have 2 into x plus 1 into n. So this term, and then here also we have x plus 1 into yn plus 1. So just take x plus 1 common. So we can write it as 2 into. So we can write 2 into x plus 1. So 2 into x plus 1, and then after that keep yn plus 1 as it is, then plus. Then after that we have, so we can split it. So n square into yn minus n into yn plus x plus 1 into yn plus 1 plus n into yn plus 4 into yn is equal to 0. So we can observe that here we have minus n into yn, here we have plus n into yn. So just cancel this both. So therefore we can write it as x plus 1 whole square into yn plus 2 plus. So therefore we had 2 into n, right? So 2 into n. So then after that it will be, so just write, so multiply these equations. So we can write it as 2n into x yn plus 1, 2n into x yn plus 1. Then again we have plus 2 into n into yn plus 1 plus. So we can write n square yn is there plus 4yn is there. So just we can write it as n square plus 4 into yn plus, this is x plus 1 yn plus 1 is equal to 0. So therefore finally we can write it as x plus 1 whole square into yn plus 2 plus, so that is, so we can write it as, so just take 2 outside, so then it will be, so just take 2 into n outside. So 2 into n, so we have x plus 1 into yn plus 1. So then here also, so plus, then it is n square plus 4 into yn. N square plus 4 into yn is equal to 0. So therefore, so we have just taken this, we have x into x plus 1 into yn plus 1. So here also we have x. So we have just taken x plus 1 common, because if you write this, if you take 2n outside, then this can be written as, so if you take 2 into n outside, then you can write it as 2 into n. So it will be x plus 1 into yn plus 1. So since here also we have common terms, here also we have common terms, we have written it only once. So just write x plus 1 whole square yn plus 2 plus. So that is, we have written 2 into n x plus 1 yn plus 1 plus. So this is n square plus 4 into yn is equal to 0. So this is the required nth derivative for the equation. So this is the nth derivative for the equation, that is sin inverse y is equal to 2 into log of x plus 1. Thank you friends. Subscribe our channel for more updates.